Now, when you're looking at the removal of the leaving group and the hydrogen in an elimination reaction, how do we determine which hydrogen will be removed? We talk about regioselectivity, which is what concerns the preference of a reaction, in this case, involving one particular proton, one particular hydrogen. The rule for elimination reactions is that the more substituted alkene tends to be the major product. So, for example, if this is your starting alcohol in this case, and we're going to do an elimination reaction, technically you could have two different products. This OH can leave with a hydrogen from this carbon or a hydrogen from this carbon. In each of those cases, you would see you'd either form a double bond here or here. And you can see those products laid out. A double bond in between, that's when you take off this hydrogen along with your OH, or a double bond on the end here. That's if you take off a hydrogen from this carbon or this carbon, either of them, they're equal in this case, to form your double bond. Now, when picking which would actually occur, we see that the major product is when this hydrogen is removed, forming a double bond in between, because this double bond is the most substituted. See, it has a methyl, a methyl, a methyl, and another methyl branched off of the double bond, as opposed to the minor product where we have a methyl group. We do have this large group here, but on the other side, there's just a hydrogen and a hydrogen. So this tetrasubstituted alkene, this is the more substituted alkene, and thus will be the major product. In another example, you can look at the product of this reaction. So here we're taking an alkyl bromide and adding a strong base. Yet again, we have a major and a minor product. The major product is this tri-substituted double bond as opposed to this di-substituted double bond. So when the bromine leaves, it's going to leave with a hydrogen to form the double bond in the elimination. And that hydrogen could come from any carbon, one carbon away. So it could be one of these hydrogens. It could be one of these hydrogens, or it could be a hydrogen on this carbon here. Notice that there are only two products. That's because if bromine leaves with a hydrogen from here or here, you get the same product. But generally, the thing that is controlling the major product here is the substitution. So this product in which it forms a double bond within the ring is more substituted. Again, look at your double bond and see that there's a carbon, a carbon, a carbon, and one hydrogen, versus this version in which you have a carbon, and two hydrogens. So again, elimination reactions will occur in a way that favors a more substituted double bond. And that's because alkenes and their stability increases with more substitution. We talked about this in our last section, 7.1, when just talking about alkenes and double bonds in general. Remember that the more substituted your double bond, the more stable you are, and that's because these carbon groups actually offer some stability via electron donation. And you actually can also have some resonance occurring between carbon groups attached to a double bond, remember, as a minor product, and where the double bond placement is. So more substitution, more stability, and that's why these elimination reactions are going to tend towards the more stable product. This rule of stability in an elimination reaction comes from Zaitsev. Generally, again, the rule is, as stated, that elimination will occur such that the hydrogen that is removed from the beta carbon with the fewest hydrogens. So here was that same example this is a similar example with a ring. Here's the carbon with the bromine on it. Now, any adjacent carbon could host the hydrogen for removal and the formation of a double bond. And you're going to then pick the carbon that has the fewest hydrogens on it. So here, this carbon has 3 hydrogens, this carbon has 2 hydrogens, and this carbon has only 1 hydrogen. So the double bond would form here, removing this hydrogen. Now, what about E or Z formation? Or also, we could use the words cis or trans formation. Remember, these are akin to each other, and we talked about them in the last section. Based on this rule, what you might expect is that the E product, or generally the trans product, would be preferentially formed because it is less sterically hindered. And experimental results support this hypothesis. So in general, the more stable trans product, or the E isomer, is formed preferentially when forming double bonds. So again, this formation, the trans formation, is going to be the major product generally when making these double bonds via elimination.